What if I told you the moon might be as far as humans ever go? Not because we gave up, not because we stopped funding NASA, but because the cosmos itself says no. In the language of light years, radiation, and time dilation. This is the video Neil deGrasse Tyson won't make. Let's talk about the prison we call the universe. But before you click away thinking this is just another doom and gloom video, hear me out. This isn't about crushing your hopes. It's about opening your eyes to the breathtaking, humbling, and sometimes terrifying reality of our cosmic situation. And here is a question for you. If you could send a message to an alien civilization, what's the first thing you would tell them? Let me know in the comments below. I'll pin the most creative answer. Now let's begin. Let's start with something that might surprise you. The farthest humans have ever traveled from Earth is roughly 400,000 kilometers. That's the distance to the moon. The Apollo astronauts achieved this feat over 50 years ago, between 1969 and 1972. Since then, no human being has ventured beyond low Earth orbit. We've been circling our own planet like goldfish swimming in a bowl, gazing out at an infinite ocean we cannot enter. Think about that for a moment. In half a century of technological advancement, smartphones, the internet, artificial intelligence, genetic engineering, we haven't pushed the boundary of human space exploration a single kilometer further. The International Space Station orbits at roughly 400 kilometers above Earth. That's 1,000 times closer than the moon. We've actually retreated, but here's where it gets truly mind-bending. Let's talk about Mars, the next logical step for human exploration. Mars, at its closest approach to Earth, sits about 54.6 million kilometers away. At its farthest, that distance stretches to 400 million kilometers. Using current propulsion technology, a one-way trip to Mars takes approximately 7 to 9 months. That's 7 to 9 months of floating through the cosmic void, exposed to dangers that would make any horror movie look tame. And Mars is our neighbor, our celestial next-door friend. In cosmic terms, Mars is so close to us that light takes only about 3 minutes to travel between our planets at closest approach. If the universe were a city, Mars would be the house at the end of your street. Yet reaching it remains one of the greatest challenges our species has ever faced. I want you to really absorb what I'm about to tell you. If you're finding this content valuable, take a second to hit that subscribe button and drop a thumbs up. It helps this channel grow and allows me to keep bringing you these deep dives into the cosmos. Your support genuinely makes a difference. The nearest star system to our Sun is Alpha Centauri, located approximately 4.37 light-years away. A light-year is the distance light travels in 1 year, moving at roughly 300,000 kilometers per second. Do the math, and Alpha Centauri sits about 40 trillion kilometers from Earth. 40 trillion. That number is so large it becomes meaningless without context. Here's the context. Voyager 1, launched in 1977, is currently the farthest human-made object from Earth. As of late 2025, it has traveled over 24 billion kilometers and is approaching a remarkable milestone. In November 2026, Voyager 1 will cross the 1 light-day threshold, meaning radio signals will take 24 hours just to reach it, and another 24 hours for any response to return. A 48-hour round-trip conversation with a machine we launched nearly 5 decades ago. Voyager 1 travels at approximately 17 kilometers per second, or around 61,000 kilometers per hour. At this speed, which is faster than any human has ever traveled, it would take Voyager 1 over 70,000 years to reach Alpha Centauri. 70,000 years. Human civilization as we know it is only about 10,000 years old. We would need to wait 7 times longer than the entire history of agriculture, cities, and written language combined just to reach the nearest star. And there's nothing special waiting for us at Alpha Centauri. No gas stations, no supply depots. No friendly aliens ready to refuel our ships, just another star system that may or may not have habitable planets. The closest potentially Earth-like exoplanet we've discovered is Proxima Centauri b, orbiting the red dwarf Proxima Centauri within the Alpha Centauri system. It sits in what scientists call the habitable zone, where liquid water could theoretically exist on its surface. But even if this world turned out to be a paradise, reaching it remains a fantasy with our current understanding of physics. Let me put this in perspective with a thought experiment. Imagine you're standing in New York City and you want to walk to Los Angeles. That's roughly 4,500 kilometers, a significant journey, but absolutely achievable. Now imagine the entire distance from New York to Los Angeles represents the distance from Earth to the Moon. Our greatest achievement, landing humans on the Moon, is equivalent to walking across America. Now, using this same scale, how far would you need to walk to reach Alpha Centauri? Prepare yourself. You would need to walk the entire circumference of Earth. Not once, not twice, but over 100 million times. The numbers become so absurd that our brains simply cannot process them. We evolved to understand distances we could walk, rivers we could cross, mountains we could climb. We did not evolve to comprehend the interstellar void. This brings us to a profound realization. The universe is not built to human scale. We are tiny creatures on a tiny world, orbiting an average star in the suburbs of an average galaxy. The Milky Way alone contains somewhere between 100 billion and 400 billion stars. The observable universe holds approximately 2 trillion galaxies. The total number of stars out there exceeds the number of grains of sand on every beach on Earth. And yet, despite this unimaginable abundance, we may be forever isolated. Not because the universe is empty, but because it is simply too big, too hostile, and too indifferent to our dreams of exploration. But distance is only one piece of this cosmic puzzle. The void between stars isn't just empty space waiting to be crossed. It's a radiation-filled death trap that would destroy human biology long before we reached any destination, and that's what we need to talk about next. Space radiation comes in several terrifying flavors. First, there's solar radiation, streams of charged particles constantly flowing from our sun. On Earth, we're protected by our planet's magnetic field and atmosphere. Step outside that protective bubble, and these particles bombard your body relentlessly. Then there's galactic cosmic radiation, high-energy particles that originate from supernova explosions, black holes, and other violent cosmic events throughout the galaxy. These particles travel at nearly the speed of light and carry enough energy to penetrate spacecraft hulls, human tissue, and even damage DNA at the molecular level. NASA has studied these effects extensively. Astronauts aboard the International Space Station receive radiation doses roughly 10 times higher than what we experience on Earth's surface. And remember, the ISS orbits within Earth's protective magnetic field. Venture beyond this shield, and the exposure skyrockets. During the Apollo missions, astronauts were fortunate. Their trips lasted only about 8 to 12 days, limiting their radiation exposure. A mission to Mars would take at least 7 months each way, plus time on the surface. That's nearly 3 years of exposure to cosmic radiation, far beyond what any human has ever experienced. The health consequences are severe. Increased cancer risk, damage to the central nervous system, potential cognitive decline, cataracts, and cardiovascular problems. A 2025 NASA study confirmed that space radiation remains one of the most significant obstacles to long-duration spaceflight. Current shielding technology simply cannot block galactic cosmic rays effectively. These particles are so energetic that they can penetrate several centimeters of aluminum, the primary material used in spacecraft construction. Some researchers have proposed using water tanks or polyethylene barriers as radiation shields. Others suggest magnetic field generators that could deflect charged particles. But none of these solutions have been proven effective for multi-year missions beyond Earth's magnetic protection. The technology simply doesn't exist yet, and developing it will require breakthroughs we cannot predict or guarantee. But radiation isn't the only biological nightmare waiting for us in the cosmic void. Your body evolved over millions of years to function in Earth's gravity. Every muscle, every bone, every organ developed under the constant pull of 9.8 meters per second squared. Take that away, and your body begins to fall apart in ways that would horrify you. Astronauts returning from 6-month stays on the International Space Station experience significant bone density loss, sometimes up to 1.5% per month in certain areas. Their muscles atrophy despite rigorous daily exercise. Their hearts, no longer needing to pump blood against gravity, begin to weaken and shrink. Their eyesight deteriorates as fluid pressure shifts toward their heads, flattening their eyeballs and damaging their optic nerves. This condition, known as spaceflight-associated neuro-ocular syndrome, affects roughly 70% of astronauts on long-duration missions, and we're only talking about 6 months in low Earth orbit. Imagine what 3 years would do to a human body traveling to Mars and back. Imagine what decades or centuries would do to generations of humans attempting to reach another star system. Some scientists propose artificial gravity as a solution. Rotating spacecraft could theoretically create centrifugal force that mimics gravity's effects. But building such vessels presents enormous engineering challenges. The rotation rate, the radius of the habitat, the structural integrity required, all of these factors make artificial gravity spacecraft extraordinarily complex and expensive. We've never built one. We've never even tested the concept with human subjects for extended periods. Then there's the psychological dimension, something we rarely discuss when dreaming about interstellar travel. Human beings are social creatures. We need sunlight, fresh air, open spaces, and connection with nature to maintain mental health. Confine a small group of people inside a metal tube for years on end, and psychological breakdown becomes almost inevitable. Studies of isolated Antarctic research stations and submarine crews reveal alarming patterns. Depression, anxiety, interpersonal conflicts, and cognitive decline all increase dramatically during long-duration isolation. The Mars 500 experiment conducted between 2010 and 2011 simulated a 520-day Mars mission with 6 crew members confined to a small habitat in Moscow. Despite being on Earth with the knowledge they could leave if truly necessary, participants experienced sleep disorders, lethargy, and psychological stress. Now multiply that duration by decades, by centuries. Generation ships, the theoretical vessels that would carry humans across interstellar distances over multiple lifetimes, would need to maintain social cohesion, psychological stability, and cultural continuity for thousands of years. No human society has ever achieved this level of stability. Empires rise and fall. Civilizations collapse. Languages evolve beyond recognition within mere centuries. How could we possibly expect a small, isolated population to maintain the knowledge, skills, and motivation needed to complete a journey lasting longer than recorded history? Speaking of which, if you want to understand just how enormous our solar system alone is, I made a video called "How Long Would It Take to Leave the Solar System?" that breaks down these distances in a way that might genuinely change how you see our cosmic neighborhood. After you finish this video, check it out. It'll give you an even deeper appreciation for why escaping our tiny corner of the universe presents such an overwhelming challenge. The link is in the description and on the card above. Now let's talk about the energy requirements for interstellar travel, because this is where the dream truly collides with the laws of physics. Moving any object through space requires energy. The faster you want to go, the more energy you need. And here's where Einstein's special relativity delivers a devastating blow to our interstellar ambitions. As an object approaches the speed of light, the energy required to accelerate it further increases exponentially. To accelerate a single kilogram of mass to 90% of light speed would require approximately 11.7 trillion megajoules of energy. For reference, the entire United States consumed approximately 93 quadrillion British thermal units of energy in 2023. Accelerating a small spacecraft to relativistic speeds would require energy production on a scale our civilization has never achieved. But let's be generous. Let's forget about reaching 90% of light speed. Let's aim for something more modest, say 10% of light speed. At this velocity, reaching Alpha Centauri would take approximately 43 years. That's within a human lifetime, at least theoretically achievable for a crew that departed in their 20s and arrived in their 60s. The problem remains energy. Even at 10% of light speed, the energy requirements are staggering. The Parker Solar Probe, launched in 2018, currently holds the record for the fastest human-made object relative to the Sun, reaching speeds of approximately 170 kilometers per second during its closest approaches. That's impressive by our standards, but it represents only 0.056% of light speed. We would need to increase our propulsion capabilities by a factor of roughly 180 just to reach 10% of light speed. Chemical rockets, the technology that carried us to the Moon, simply cannot achieve these velocities. The fundamental problem is the rocket equation, developed by Konstantin Tsiolkovsky in 1897. This equation shows that to accelerate a spacecraft to higher velocities, you need exponentially more fuel. But that additional fuel has mass, which requires even more fuel to accelerate. Beyond a certain point, you're essentially trying to lift fuel with more fuel, and the whole concept breaks down. Nuclear propulsion offers some improvement. Project Orion, conceived in the late 1950s, proposed using nuclear explosions to propel spacecraft. Small atomic bombs would be detonated behind the ship, pushing it forward with each blast. Theoretical calculations suggested Orion could achieve velocities of 3 to 5% of light speed. But the concept was abandoned due to the Partial Nuclear Test Ban Treaty of 1963 and concerns about radioactive contamination. More recently, scientists have explored nuclear thermal propulsion and nuclear electric propulsion systems. These technologies could significantly reduce travel times within our solar system, potentially cutting a Mars journey from 7 months to 3 or 4 months. But even these advanced concepts fall far short of the velocities needed for interstellar travel. Ion engines represent another incremental improvement. These systems accelerate charged particles to high velocities, producing small but continuous thrust over extended periods. NASA's Dawn spacecraft used ion propulsion to visit the asteroid Vesta and the dwarf planet Ceres. But ion engines produce thrust measured in fractions of a newton, barely enough to lift a piece of paper on Earth. While efficient for long-duration missions within our solar system, they cannot provide the acceleration needed for interstellar journeys. What about solar sails? This elegant concept uses the pressure of sunlight itself to accelerate a spacecraft. Photons, despite having no mass, carry momentum. When they strike a reflective surface, they transfer this momentum, producing a tiny but persistent push. The Planetary Society successfully demonstrated solar sailing with their light sail missions in 2015 and 2019. The breakthrough Starshot initiative, announced in 2016 and backed by the late physicist Stephen Hawking and billionaire Yuri Milner, proposed using powerful ground-based lasers to accelerate small, lightweight probes to 20% of light speed. At this velocity, the probes could reach Alpha Centauri in approximately 20 years. The concept is theoretically sound, but faces enormous technical challenges. The probes would need to be incredibly small, weighing only a few grams to achieve the required acceleration. They would carry no humans, only miniaturized instruments capable of photographing any planets they encounter. The laser array required would need to generate approximately 100 gigawatts of power, roughly equivalent to the total electricity consumption of a medium-sized country. Building such an array would cost tens of billions of dollars and require international cooperation on an unprecedented scale. And even if breakthrough Starshot succeeds, it would only send tiny robotic probes on one-way trips. No humans, no return journey, no possibility of colonization. We would receive images of Alpha Centauri approximately 25 years after launch, assuming the probes survive the journey and successfully transmit their data across 4 light-years of space. This brings us to a critical distinction that often gets lost in popular discussions of space travel. Sending robots is fundamentally different from sending humans. Robots don't need food, water, air, or psychological support. They don't get cancer from radiation exposure. They don't suffer bone loss in microgravity. They can be miniaturized, mass-produced, and considered expendable. Every robotic mission we've sent beyond Earth orbit has taught us something valuable. The Voyager probes continue transmitting data from interstellar space nearly 5 decades after launch. The Mars rovers have revolutionized our understanding of the Red Planet. The New Horizons spacecraft gave us our first close-up images of Pluto in 2015 before continuing toward the Kuiper Belt. But there's something fundamentally human about wanting to go ourselves. We don't just want to see pictures of distant worlds. We want to stand on alien soil, breathe alien air, and experience the profound loneliness and wonder of being truly far from home. This desire runs deep in our species, perhaps encoded in the same genes that drove our ancestors out of Africa to colonize every continent on Earth. The tragedy is that the universe may not care about our desires. Physics doesn't negotiate. The speed of light isn't a speed limit we can eventually break with better technology, like the sound barrier was broken by Chuck Yeager in 1947. The speed of light is woven into the fabric of space-time itself. It's the cosmic speed limit, the rate at which causality propagates through the universe. Nothing with mass can ever reach the speed of light. This isn't an engineering limitation we might overcome with better rockets or more funding. It's a fundamental property of the universe we inhabit. As any object with mass accelerates toward light speed, its relativistic mass increases. At 99% of light speed, an object's effective mass has increased by a factor of 7. At 99.9%, it's increased by a factor of 22. At 99.99%, by a factor of 70. The closer you get, the more energy you need, approaching infinity as you approach light speed. This means that accelerating even a modest spacecraft to the speed of light would require infinite energy. Not a lot of energy. Not more energy than currently exists. Infinite energy. The mathematics is unambiguous. The speed of light represents an absolute barrier that no amount of technological progress can overcome within our current understanding of physics. Now, some will point to theoretical concepts like the Alcubierre drive, often called a warp drive in science fiction. In 1994, Mexican physicist Miguel Alcubierre proposed a mathematical solution to Einstein's field equations that would allow faster-than-light travel. The concept doesn't violate relativity in a technical sense because the spacecraft itself wouldn't be moving through space faster than light. Instead, space itself would contract in front of the ship and expand behind it, carrying the vessel along like a surfer riding a wave. It's a beautiful idea. It's also almost certainly impossible. The Alcubierre drive would require exotic matter with negative energy density, a substance that has never been observed and may not exist. Early calculations suggested the energy requirements would exceed the total mass energy of the observable universe. Later refinements reduced these estimates significantly, but even optimistic projections require energy equivalent to the mass of Jupiter converted entirely into energy via Einstein's famous equation. We have no mechanism for achieving such conversion, and even if we did, containing and directing that energy would present insurmountable challenges. Furthermore, subsequent analysis revealed fundamental problems with the Alcubierre concept. The warp bubble would accumulate high-energy particles during transit, releasing them in a catastrophic burst upon arrival. Anything in the destination area would be annihilated. The occupants of the spacecraft would have no way to control the bubble from inside, meaning they couldn't steer, slow down, or even send signals to the outside universe. They would be trapped in a bubble of warped space-time, hurtling toward a destination they cannot change. Wormholes present another theoretical possibility. These hypothetical tunnels through space-time could theoretically connect distant points in the universe, allowing instantaneous travel across cosmic distances. Einstein's general relativity permits their existence mathematically. The problem is that every stable wormhole solution we've discovered requires exotic matter to hold it open. Without this exotic matter, any wormhole would collapse instantly, crushing anything attempting to pass through. Even if we could somehow create and stabilize a wormhole, we would need to physically transport one end to our destination before we could use it as a shortcut. This creates a paradox. We need faster-than-light travel to set up our faster-than-light travel system. It's like needing a bridge to build a bridge. The honest truth is that our current understanding of physics offers no plausible pathway to faster-than-light travel. Every concept that has been seriously analyzed either violates known physical laws, requires materials that don't exist, or demands energy on scales beyond anything our civilization could produce. This doesn't mean faster-than-light travel is absolutely impossible. Science has surprised us before, but betting humanity's future on discovering entirely new physics that contradicts our most successful theories seems unwise at best and delusional at worst. So where does this leave us? If we cannot travel faster than light, we must accept that interstellar journeys will take decades, centuries, or millennia depending on our destination. We must confront the possibility that the stars are simply too far away for human beings to reach within individual lifetimes. Some visionaries have proposed generation ships as a solution. These massive spacecraft would carry entire communities of humans on journeys lasting hundreds or thousands of years. The original crew would live and die aboard the ship, raising children who would continue the mission. Generations would pass, each one bringing the vessel slightly closer to its destination. Eventually, descendants of the original travelers, people who had never seen Earth, would arrive at a new star system and attempt to colonize whatever worlds they found there. The concept has inspired countless science fiction stories, from Heinlein's Universe to more recent works like Kim Stanley Robinson's Aurora. But the practical challenges are almost incomprehensible. A generation ship would need to be entirely self-sufficient. It couldn't resupply, it couldn't call for help. Every gram of food, every drop of water, every molecule of oxygen would need to be recycled indefinitely. The ship would essentially be a miniature planet, a closed ecosystem capable of supporting human life for centuries without any external input. We've attempted small-scale versions of this concept on Earth. Biosphere 2, constructed in Arizona in the late 1980s, was designed as a closed ecological system that could support 8 humans indefinitely. The experiment failed. Oxygen levels dropped dangerously, carbon dioxide accumulated, crops failed, ants and cockroaches overran the facility. The crew members lost weight and experienced conflict. The project was eventually abandoned as a demonstration of self-sufficient habitation. If we couldn't maintain a closed ecosystem on Earth with abundant sunlight, stable temperatures, and the ability to open a door if things went wrong, how could we possibly succeed aboard a spacecraft traveling through the interstellar void? The psychological challenges might prove even more daunting than the technical ones. Imagine being born aboard a generation ship. You never chose this journey. You never saw Earth. You will never see your destination. Your entire life will be spent inside metal corridors, breathing recycled air, knowing that your existence serves only to produce the next generation of travelers. Your children will face the same fate, as will their children, for century after century. What happens when someone decides they don't want to continue the mission? What happens when factions develop, when religions emerge, when the original purpose of the journey fades into myth and legend? Human societies have never maintained unified purpose across such timescales. The generation ship would need governance systems, educational institutions, and cultural practices capable of preserving mission-critical knowledge and motivation for longer than any civilization in human history has survived. And even if somehow a generation ship completed its journey, what would await the travelers at their destination? Proxima Centauri b, the closest potentially habitable exoplanet, orbits a red dwarf star prone to violent flares. These stellar outbursts could strip away any atmosphere the planet might possess and bombard its surface with lethal radiation. The planet is likely tidally locked, meaning one side permanently faces its star while the other remains in eternal darkness. Surface conditions could be extremely hostile to Earth-evolved life. We have no guarantee that any star system within reach contains a planet suitable for human colonization. We might send generation ships on thousand-year journeys only to discover that their destinations are barren, toxic, or otherwise uninhabitable. The travelers would have no way to return. They would be stranded, their sacrifice ultimately meaningless. This brings us to perhaps the most sobering consideration of all. Even if we solved every technical problem, even if we developed propulsion systems capable of reaching significant fractions of light speed, even if we built generation ships that could maintain human civilization across millennia, we would still face a fundamental question. Why? Why should we send humans to other star systems when robotic probes could accomplish the same scientific objectives at a fraction of the cost and risk? Why should we condemn generations of humans to lives aboard spacecraft when they could live fulfilling lives here on Earth? What exactly are we hoping to achieve? The traditional answer involves species survival. If humanity remains confined to a single planet, a single asteroid impact, supervolcano eruption, or pandemic could wipe us out entirely. Spreading to multiple worlds, the argument goes, would ensure our long-term survival. But this argument has limitations. Colonizing other planets in our solar system, while enormously challenging, could provide the redundancy we need without requiring interstellar travel. Mars, despite its harsh conditions, sits only months away by spacecraft. We could potentially establish self-sufficient colonies there within centuries. The moons of Jupiter and Saturn offer additional possibilities. We don't need to reach other stars to become a multi-planetary species. Furthermore, the timescales involved in interstellar colonization are so vast that they might not provide the protection we seek. If an extinction-level event threatened Earth tomorrow, we couldn't evacuate to Alpha Centauri. The journey would take generations. By the time any colony became self-sufficient, thousands of years would have passed. For practical purposes of species survival, interstellar colonies would be so distant in both space and time that they might as well exist in a parallel universe. There's also a philosophical dimension to consider. When we imagine future humans arriving at distant star systems, we tend to assume they would still be recognizably human. But evolution doesn't stop. Isolated populations diverge over time. A colony separated from Earth by light years of distance and centuries of travel would inevitably develop its own culture, its own language, its own values. Given enough time, they might even become biologically distinct from Earth humans, adapting to the unique conditions of their new home. Are we truly ensuring humanity's survival if the beings who eventually populate the galaxy bear no resemblance to us? Or would we simply be seeding the cosmos with our descendants, creatures as different from modern humans as we are from our ancient ancestors? The answer depends on how you define humanity, whether you see it as a biological category or something more abstract, a torch of consciousness passed from generation to generation. These questions have no easy answers. They force us to confront our deepest assumptions about identity, purpose, and meaning. And perhaps that's the real value of contemplating interstellar travel, not as a practical goal, but as a thought experiment that illuminates who we are and what we value. But let's return to the concrete obstacles, because we haven't yet discussed one of the most insidious challenges facing any long-duration space mission: the spacecraft itself. Everything degrades over time. Metal fatigues, seals crack, electronics fail, lubricants evaporate. Micrometeorites slowly erode exterior surfaces. A spacecraft designed for a multi-century journey would need to withstand forces and timescales far beyond anything we've ever engineered. Consider the Voyager probes once more. Launched in 1977, they continue operating nearly 50 years later, a remarkable achievement in engineering longevity, but they're also failing. Their power sources, radioisotope thermoelectric generators that convert heat from decaying plutonium into electricity, produce less energy each year. By the early 2030s, Voyager 1 will likely lack sufficient power to operate any scientific instruments. By 2036, it may fall silent entirely. 50 years, that's how long our most durable spacecraft have lasted. A journey to Alpha Centauri at 10% of light speed would take over 400 years. At more realistic velocities, we're talking millennia. How do you build something that functions for 1,000 years? Medieval cathedrals have stood for centuries, but they required constant maintenance, repairs, and renovations. They didn't need to maintain life support systems, navigate through space, or protect their occupants from cosmic radiation. A generation ship would need to be simultaneously a cathedral, a farm, a hospital, a factory, and a spaceship, all functioning perfectly for longer than any human structure has ever lasted, without continuous external support. The materials science challenges alone are staggering. We would need alloys that resist fatigue over millennia. We would need electronics hardened against radiation far beyond current capabilities. We would need mechanical systems with lubrication that doesn't degrade, seals that don't crack, and moving parts that don't wear out. We would need redundancy upon redundancy, backup systems for our backup systems, with the manufacturing capability to produce replacement components using only materials available aboard the ship. This last point deserves emphasis. A generation ship couldn't rely on spare parts brought from Earth. Over centuries, every component would eventually fail and need replacement. The ship would need to be a complete industrial civilization in miniature, capable of mining raw materials from its own structure or collected during the journey, refining them into usable forms and manufacturing whatever components required replacement. We've never built anything remotely approaching this level of self-sufficiency. Modern supply chains span the entire globe. A smartphone contains materials from dozens of countries, processed through hundreds of specialized facilities, assembled with precision equipment that itself required years to develop and build. Replicating this manufacturing capability aboard a spacecraft seems almost inconceivable with current technology. Three-dimensional printing offers some hope, Additive manufacturing has advanced rapidly in recent decades, allowing increasingly complex objects to be fabricated from digital designs. NASA has experimented with three-dimensional printing aboard the International Space Station, successfully manufacturing tools and spare parts in microgravity. Future developments might allow spacecraft to produce most components on demand, reducing the need for extensive spare parts inventories. But three-dimensional printers themselves require maintenance. They need raw materials. They can produce objects only within their design specifications. For truly long-duration missions, we would need printers capable of printing other printers, manufacturing systems that can reproduce themselves across generations. This approaches the realm of von Neumann machines, self-replicating systems that exist only in theory and science fiction. Let's also consider the energy requirements for a multi-century voyage. The spacecraft would need continuous power for life support, navigation, communication, manufacturing, and countless other systems. Solar panels become useless beyond the outer solar system, where sunlight dwindles to insignificance. Nuclear fission reactors have operational lifespans measured in decades, not centuries. Nuclear fusion remains experimental and may never be practical for spacecraft propulsion or power generation. Radioisotope thermoelectric generators, like those powering the Voyager probes, offer reliable power for decades but gradually decline as their radioactive fuel decays. A spacecraft relying on plutonium-238, the isotope used in most space RTGs, would see its power output drop by half every 87.7 years. After several centuries, virtually no power would remain. Some theorists have proposed antimatter as a solution. When matter and antimatter meet, they annihilate completely, converting their entire mass into energy according to Einstein's famous equation. 1 gram of antimatter reacting with 1 gram of matter would release approximately 170 trillion joules of energy, equivalent to about 43 kilotons of TNT. In theory, small amounts of antimatter could power a spacecraft for centuries. The problem is production and storage. We currently produce antimatter in particle accelerators, 1 atom at a time, at enormous energy cost. The total amount of antimatter ever produced by humanity amounts to mere nanograms. Scaling up production to useful quantities would require energy inputs far exceeding what we could ever recover from the antimatter itself. And storing antimatter presents nightmarish challenges since it annihilates on contact with ordinary matter. Any containment failure would result in catastrophic explosion. These engineering challenges compound upon each other. Each problem we solve reveals new problems beneath. Each solution requires technologies that don't yet exist, materials we haven't discovered, or energy sources we cannot produce. The path to interstellar travel isn't blocked by a single, insurmountable obstacle, but by an endless series of obstacles, each one sufficient to halt our progress indefinitely. And yet, despite all these challenges, humanity continues to dream. We continue to look up at the stars and wonder what lies beyond our tiny corner of the cosmos. This persistent curiosity, this refusal to accept limitations, defines our species as much as our biological constraints. Perhaps that's the most important thing to understand about our cosmic situation. We are creatures of contradiction. We evolved on a single planet, yet dream of conquering the galaxy. We live for decades, yet imagine journeys lasting millennia. We understand the physics that imprisons us, yet refuse to abandon hope of escape. This tension between aspiration and limitation has driven every great achievement in human history. The Wright brothers were told heavier-than-air flight was impossible. Alan Turing imagined thinking machines when computers filled entire rooms. Scientists once believed the sound barrier represented an absolute limit to aircraft speed. In each case, determined individuals found ways around seemingly insurmountable obstacles. They didn't violate the laws of physics. They discovered new applications of those laws, found clever workarounds, or simply refused to accept that the current state of technology represented the final word. Could the same happen with interstellar travel? Could some future Einstein discover loopholes in relativity that permit faster-than-light travel? Could breakthrough propulsion technologies reduce journey times from millennia to years? Could we develop hibernation techniques allowing humans to sleep through centuries of travel? The honest answer is that we don't know. Science has surprised us before, and it would be arrogant to claim we've discovered everything there is to know about the universe. Our current theories, as successful as they are, remain incomplete. We still don't understand how to reconcile quantum mechanics with general relativity. We don't know what dark matter and dark energy actually are, despite them comprising approximately 95% of the universe's total content. We haven't developed a theory of quantum gravity that might reveal entirely new possibilities for manipulating spacetime. History teaches humility. In 1895, Lord Kelvin reportedly declared that heavier-than-air flying machines were impossible. 8 years later, the Wright brothers proved him wrong. In 1933, Ernest Rutherford, the physicist who discovered the atomic nucleus, called the idea of extracting energy from atoms moonshine. 12 years later, nuclear weapons ended World War II. Predicting what future science might achieve has proven notoriously difficult, but history also teaches caution. For every technological barrier that eventually fell, others have stood firm. We still cannot transmute lead into gold economically, despite centuries of alchemical dreams. We still cannot achieve perpetual motion, despite countless attempts by inventors who refused to accept thermodynamic limitations. Some barriers exist because of fundamental physical laws that no amount of cleverness can circumvent. The speed of light appears to be such a barrier. Unlike the sound barrier, which was an engineering challenge involving fluid dynamics and materials science, the light speed limit emerges from the basic structure of spacetime itself. Breaking it wouldn't just require better technology, it would require the universe to operate differently than our most precisely verified theories predict. This doesn't mean we should abandon hope entirely, it means we should calibrate our expectations realistically. Interstellar travel, if it ever becomes possible, will likely be far more difficult, far more expensive, and far slower than science fiction has led us to believe. The galaxy will not be explored by dashing captains in sleek starships. It will be explored, if at all, by patient generations willing to sacrifice everything for a destination they will never see. And perhaps that's okay. Perhaps the value of reaching for the stars lies not in actually grasping them, but in the reaching itself. The technologies we develop while attempting interstellar travel might transform life here on Earth. The perspective we gain from contemplating our cosmic isolation might make us better stewards of our home planet. The humility we learn from confronting the universe's vastness might help us resolve the petty conflicts that threaten our civilization. Let me share something that might shift your perspective on this entire discussion. We tend to frame space exploration in terms of human ambition, human achievement, human destiny. But the universe doesn't care about human ambition. The stars aren't waiting for us. The cosmos has no obligation to be navigable by creatures who evolved to chase antelope across African savannas. When we complain that the universe is too big, we're essentially complaining that reality doesn't conform to our preferences. But why should it? We are products of this universe, shaped by its laws, constrained by its parameters. The distances between stars aren't obstacles placed in our path by a malevolent designer. They're simply features of a cosmos that existed for billions of years before us and will continue for trillions of years after we're gone. From this perspective, our cosmic isolation isn't a tragedy. It's simply the natural condition of intelligent life in a vast universe. Every technological civilization that has ever arisen anywhere in the cosmos has faced the same barriers we face. The speed of light constrains everyone equally. The distances between stars humble all travelers, regardless of their biology or technology. This realization connects us to something larger than ourselves. Somewhere out there, perhaps in another galaxy entirely, another civilization might be having this exact same conversation. They might be staring at their own night sky, contemplating the impossibility of reaching stars that appear tantalizingly close, yet remain forever beyond reach. They might be feeling the same mixture of wonder and frustration that we feel, the same longing for connection across the cosmic void. We are all prisoners of the same physics. We are all children of the same universe, and somehow that shared condition makes the loneliness a little more bearable. But let's not surrender to melancholy just yet, because while interstellar travel may remain beyond our reach, there's still an entire solar system waiting to be explored. And what a solar system it is! Our cosmic neighborhood contains wonders that would have seemed impossible to previous generations. Mars, with its ancient river valleys and polar ice caps, hints at a wetter, warmer past when life might have flourished. Europa, a moon of Jupiter, hides a liquid water ocean beneath its icy crust, kept warm by tidal heating from Jupiter's immense gravity. Enceladus, a tiny moon of Saturn, shoots geysers of water vapor into space, suggesting another subsurface ocean that could potentially harbor life. Titan, Saturn's largest moon, possesses a thick atmosphere and liquid hydrocarbon lakes on its surface. It's the only body in the solar system besides Earth with stable liquid on its surface. The chemistry happening there, while not water-based, might represent an entirely different approach to the origin of life. Even asteroids and comets hold secrets worth discovering. These primordial remnants preserve materials from the solar system's formation 4.6 billion years ago. Studying them reveals the conditions that gave birth to our Sun, our planets, and ultimately ourselves. Some asteroids contain valuable minerals that might one day be mined, providing resources for space-based construction and reducing pressure on Earth's dwindling reserves. We could spend centuries exploring our solar system without exhausting its mysteries. We could establish research stations on the Moon, colonies on Mars, mining operations in the asteroid belt, and scientific outposts around the gas giants. We could learn things about planetary formation, about the origins of life, about the fundamental nature of matter and energy that would transform our understanding of the cosmos. And all of this is achievable with technologies that exist today, or could be developed within decades. We don't need faster-than-light travel to explore our solar system. We don't need generation ships or warp drives or wormholes. We need political will, economic investment, and the patience to pursue long-term goals that may not pay off within a single election cycle. This is the paradox of our moment in history. We possess the capability to become a truly spacefaring civilization, to establish permanent human presence beyond Earth, to ensure our survival against planetary catastrophes. Yet we remain largely earthbound, distracted by short-term concerns, unable to muster the collective determination that characterized the Apollo era. Perhaps our obsession with interstellar travel is actually counterproductive. By dreaming of stars we cannot reach, we neglect the worlds within our grasp. By fantasizing about starships, we fail to fund the rockets that could take us to Mars. By imagining contact with alien civilizations, we overlook the alien life that might exist within our own solar system, swimming in subsurface oceans or drifting in the clouds of Venus. The universe has given us a magnificent gift, a solar system rich with possibilities, diverse enough to keep us busy for millennia, close enough to explore with technologies we already understand. Maybe we should appreciate this gift before complaining that we didn't receive more. This brings us to another consideration that rarely enters discussions of space exploration, the question of what we might call cosmic timing. We happen to exist at a particular moment in the universe's history, and that timing profoundly shapes what's possible for us. The universe is approximately 13.8 billion years old. Our Sun formed about 4.6 billion years ago. Complex life on Earth arose only about 500 million years ago. Human civilization is roughly 10,000 years old. We've possessed the technology to leave our planet for less than 70 years. In cosmic terms, we just woke up. We're newborns, barely conscious, taking our first tentative steps into a universe that has been evolving for eons without us. Is it any surprise that we haven't figured out interstellar travel yet? Would you expect a toddler to run marathons? Some scientists speculate that truly advanced civilizations, those millions or billions of years older than ours, might have developed technologies we cannot even imagine. They might have solved problems we don't yet know exist. They might travel between stars as easily as we travel between cities. From their perspective, our struggles with interstellar travel might seem quaint, like watching ancient humans try to cross oceans on log rafts. But if such civilizations exist, where are they? This question, famously posed by physicist Enrico Fermi during a lunch conversation in 1950, has haunted scientists for decades. Given the age and size of the universe, given the billions of potentially habitable planets in our galaxy alone, intelligent life should have arisen countless times. Some of those civilizations should have developed interstellar travel millions or billions of years ago. They should have colonized the entire galaxy by now, yet we see no evidence of them. This discrepancy between expectation and observation is called the Fermi Paradox, and it has profound implications for our own prospects. Perhaps interstellar travel is simply impossible for any civilization, no matter how advanced. Perhaps the speed of light truly represents an absolute barrier that no amount of technological progress can overcome. Perhaps every intelligent species in the universe is confined to its home star system, able to observe the cosmos, but never to explore it. This interpretation of the Fermi Paradox suggests that our isolation isn't a temporary condition we might eventually overcome. It's the permanent fate of all intelligent life everywhere. The universe may be teeming with civilizations, each one trapped on its own island, gazing across unbridgeable gulfs at neighbors it will never meet. Alternatively, perhaps interstellar travel is possible but extremely rare. Perhaps the challenges are so immense that only a tiny fraction of civilizations ever attempt it. Perhaps most intelligent species decide sensibly that the costs outweigh the benefits. Why spend millennia traveling to another star system when you could spend those same resources making your homeworld paradise? Or perhaps advanced civilizations do exist and have colonized the galaxy, but they're avoiding us deliberately. This is the zoo hypothesis, which suggests that alien observers keep their distance, allowing younger civilizations to develop without interference. We might be living in a cosmic nature preserve, watched by beings who find us interesting but not worth contacting. Each proposed solution to the Fermi Paradox carries unsettling implications. If interstellar travel is impossible, we're alone forever, no matter how many civilizations exist elsewhere. If it's possible but rare, we face enormous challenges that most species fail to overcome. If advanced aliens are watching us, our entire conception of our place in the universe requires revision. There's another possibility, darker than the rest. Perhaps civilizations that develop advanced technology inevitably destroy themselves before achieving interstellar travel. Perhaps nuclear weapons, artificial intelligence, engineered pandemics, or environmental collapse represent filters that eliminate technological species with grim regularity. Perhaps the galaxy is littered with the ruins of civilizations that reached our level of development and then vanished, unable to survive their own power. This great filter hypothesis suggests that the rarity of observable alien civilizations might reflect not the difficulty of interstellar travel, but the difficulty of surviving long enough to attempt it. If the filter lies behind us in the emergence of life or the evolution of intelligence, then we've already beaten the odds and might have a bright future ahead. If the filter lies ahead of us in some challenge we haven't yet faced, then our long-term prospects are grim indeed. Looking at human history, it's hard to feel optimistic. We've come terrifyingly close to nuclear annihilation multiple times. Climate change threatens to destabilize our civilization within the coming century. Emerging technologies like artificial intelligence and genetic engineering pose risks we don't fully understand. Our species has demonstrated remarkable ingenuity, but also remarkable capacity for self-destruction. Perhaps the reason we haven't encountered alien visitors is that no civilization survives long enough to send them. Perhaps the development of technology capable of interstellar travel inevitably coincides with the development of technology capable of species-wide suicide. Perhaps the same curiosity and ambition that drive scientific progress also drive the conflicts that end civilizations. This interpretation suggests that our obsession with reaching the stars might be misplaced. Before worrying about whether we can cross interstellar distances, perhaps we should worry about whether we can survive the next few centuries. Before dreaming of colonizing other worlds, perhaps we should focus on not destroying this one. And yet I can't help but feel that these two goals are connected. A civilization capable of interstellar travel would necessarily have solved many of the problems currently threatening our survival. They would have developed sustainable energy sources. They would have learned to cooperate across political and cultural boundaries. They would have achieved a level of technological maturity that implies social and ethical maturity as well. Perhaps the path to the stars runs through our own hearts. Perhaps the greatest obstacles to interstellar travel aren't physical but psychological, not the speed of light, but the limitations of human nature. Perhaps we need to become better versions of ourselves before the universe will allow us to explore its depths. This is speculative, of course. The universe doesn't dispense rewards for good behavior. Physics doesn't care whether we've learned to live in peace. But there might be practical connections between social development and technological capability that make ethical progress a prerequisite for interstellar travel. Consider the resources required for any serious interstellar mission. We're talking about investments that would dwarf the Apollo program, projects requiring decades or centuries of sustained commitment. No single nation could accomplish this alone. It would require international cooperation on an unprecedented scale, the pooling of resources and expertise from across human civilization. Such cooperation seems impossible in our current world of competing nations, conflicting ideologies, and short-term thinking. But perhaps it won't always be impossible. Perhaps future generations will look back at our era of division and conflict the way we look back at medieval religious wars, as a primitive stage we eventually outgrew. Perhaps the very process of attempting interstellar travel will force us to develop the cooperative institutions we need. There's a beautiful circularity to this idea. We cannot reach the stars until we learn to work together. But reaching for the stars might be exactly what teaches us to work together. The goal and the path become inseparable, each one requiring and enabling the other. This brings me to what I consider the most important insight of this entire discussion. The value of contemplating interstellar travel lies not in any practical benefits it might eventually provide. It lies in what the contemplation itself does to us. When you truly absorb the scale of the universe, when you genuinely understand your place in the cosmic story, something shifts inside you. The petty concerns of daily life recede. The conflicts between nations seem absurd. The boundaries we draw between races, religions, and cultures reveal themselves as arbitrary lines on a tiny sphere orbiting an unremarkable star in the suburbs of an average galaxy. You are made of atoms forged in stellar furnaces. The calcium in your bones was created in supernova explosions. The iron in your blood came from dying stars. You are, quite literally, the universe contemplating itself. Every human being who has ever lived shares this cosmic heritage. We are all stardust, all children of the same cosmic processes, all temporary patterns in an infinite dance of matter and energy. This perspective doesn't solve the engineering challenges of interstellar travel. It doesn't make the distances shorter or the physics more forgiving. But it does something perhaps more valuable. It reminds us why the question matters in the first place. It connects us to something larger than our individual lives, larger even than our species. It situates human existence within a context so vast that our usual categories of meaning begin to dissolve. And perhaps that dissolution is precisely what we need. Perhaps our inability to reach the stars is itself a kind of teaching, a cosmic lesson in humility that we desperately need to learn. We have spent centuries believing ourselves the center of creation, the pinnacle of existence, the purpose for which the universe was made. Science has systematically dismantled these illusions, revealing us to be inhabitants of a small planet orbiting a medium-sized star in the outskirts of one galaxy among trillions. The impossibility of interstellar travel might be the final lesson in this cosmic education. We are not destined to conquer the galaxy. We are not fated to spread across the stars like some cosmic virus, remaking every world in our image. We are Earthlings, children of this particular planet, adapted to its particular conditions, perhaps forever confined to its immediate cosmic neighborhood. For some, this realization brings despair. If we cannot reach the stars, what's the point of anything? If human civilization will eventually end, confined to a single solar system in a universe of trillions of galaxies, doesn't that render all our achievements meaningless? I want to suggest a different response. Meaning doesn't require eternity. A sunset isn't less beautiful because it fades. A symphony isn't less moving because it ends. A human life isn't less valuable because it's finite. Perhaps human civilization is the same, a brief flowering of consciousness in a vast and ancient cosmos, precious precisely because it won't last forever. The Japanese have a concept called mono no aware, often translated as the pathos of things. It refers to a bittersweet awareness of impermanence, a gentle sadness that arises from understanding that all things must pass. This awareness doesn't diminish beauty, it enhances it. The cherry blossoms are more precious because they fall. The autumn leaves are more vivid because they signal winter's approach. Perhaps we should approach our cosmic situation with this same sensibility. We exist for a brief moment in the universe's history. We will never know most of what there is to know. We will never see most of what there is to see, and that's okay. Our limitations don't diminish our existence. Yeah, they define it. They make us who we are. A being that could travel anywhere instantaneously, that could live forever, that could know everything, would not be human. It would be something else entirely, perhaps something greater, perhaps something lesser, but certainly something different. Our finitude isn't a flaw to be overcome. It's an essential feature of our existence, the constraint that gives shape and meaning to our lives. This doesn't mean we should stop exploring. Quite the opposite. It means our explorations become more precious, more urgent, more meaningful. Every new discovery is a gift. Every glimpse of a distant world is a privilege. Every moment of wonder, staring up at stars we will never reach, is itself a form of connection with the cosmos. We may never walk on planets orbiting other stars, but we can see them, we can study them, we can imagine what it might be like to stand on their surfaces and watch alien suns rise over unfamiliar horizons. Our imaginations can travel where our bodies cannot. Our instruments can reach across distances our spacecraft never will. In this sense, we are already interstellar beings. Our consciousness extending far beyond the physical limits of our existence. The James Webb Space Telescope, launched on December 25, 2021, represents humanity's most powerful eye on the distant universe. It has captured images of galaxies forming in the early universe over 13 billion years ago. It has analyzed the atmospheres of exoplanets, detecting water vapor and other molecules that hint at conditions potentially suitable for life. It has revealed cosmic structures of breathtaking beauty and complexity, nebulae and star clusters, and colliding galaxies that dwarf anything in human experience. When you look at a James Webb image, you are seeing light that has traveled for billions of years across incomprehensible distances, light that left its source before Earth even existed, light that has finally completed its journey by entering your eyes and triggering patterns of neural activity in your brain. In that moment, you and the distant cosmos are connected. Information has flowed from there to here, from then to now, bridging gulfs of space and time that no physical traveler could ever cross. This is a form of interstellar travel, perhaps the only form we will ever achieve. Not the transportation of bodies, but the transmission of information. Not physical presence, but conscious awareness. Not being there, but knowing about there. And in some ways, this might be enough. Consider what we've learned about the universe without ever leaving our solar system. We've discovered that the cosmos began in a hot, dense state approximately 13.8 billion years ago and has been expanding ever since. We've mapped the cosmic microwave background radiation, the afterglow of the Big Bang itself. We've detected gravitational waves from colliding black holes and neutron stars, ripples in spacetime predicted by Einstein a century ago. We've discovered thousands of exoplanets orbiting other stars, some of them potentially habitable. We've analyzed the compositions of distant atmospheres using spectroscopy, identifying molecules that could indicate the presence of life. We've observed supermassive black holes at the centers of galaxies, monsters millions or billions of times more massive than our Sun, bending space-time so severely that not even light can escape their gravitational pull. All of this knowledge was gathered without sending humans beyond the Moon. All of it was achieved through the patient work of scientists using instruments based on Earth or in Earth orbit. Our inability to travel to these phenomena hasn't prevented us from understanding them. We have become cosmic beings through knowledge rather than through physical exploration. Perhaps this is the destiny of intelligent life everywhere. Perhaps every civilization in the universe eventually reaches the same conclusion we are approaching now. That the stars are too far, the journeys too long, the obstacles too great for physical travel, but that knowledge can flow where bodies cannot. Perhaps the galaxy is filled with minds contemplating the same cosmos, sharing the same insights, connected not by starships, but by the universal language of mathematics and physics. This vision has its own kind of beauty. Instead of a galaxy conquered and colonized by expanding civilizations, imagine a galaxy of contemplatives, each one gazing outward from its island of light, each one accumulating understanding, each one contributing to a universal archive of cosmic knowledge that no single species could ever complete alone. We may never meet these other minds directly. We may never exchange greetings across the interstellar void, but we share something with them nonetheless. We share the same universe, the same physics, the same fundamental questions about existence and meaning. In contemplating these questions, we join a communion of intelligence that transcends the barriers of space and time. This is not the future we imagined when we first looked up at the stars and dreamed of traveling among them. It's quieter, more contemplative, less dramatic than the visions of science fiction, but it might be more realistic. And in its own way, it might be just as profound. Let's shift our attention now to something more immediate, something that might actually be achievable within the lifetimes of people alive today. because while interstellar travel remains a distant dream, there are concrete steps we could take right now to expand human presence beyond Earth. The Artemis program, NASA's initiative to return humans to the Moon, represents the most ambitious crewed space exploration effort since Apollo. Artemis aims not just to land astronauts on the lunar surface, but to establish a sustainable human presence there. The Gateway, a planned space station in lunar orbit, would serve as a staging point for surface missions, and eventually for expeditions deeper into the solar system. The Moon, despite being our closest celestial neighbor, still holds countless secrets waiting to be uncovered. Its south polar region, where permanently shadowed craters may contain billions of tons of water ice, represents a particularly compelling target. This water could sustain lunar inhabitants, provide oxygen for breathing, and be split into hydrogen and oxygen for rocket fuel. A lunar base with access to water ice could become genuinely self-sufficient, reducing dependence on expensive resupply missions from Earth. But the Moon is just the beginning. Mars remains the ultimate near-term goal for human space exploration, the world most likely to host permanent human settlements within the coming century. Despite all the challenges I've described, radiation, microgravity, psychological stress, engineering complexity, Mars is still incomparably closer and more accessible than any star system. At its closest approach, Mars sits roughly 55 million kilometers from Earth. That's far, certainly. About 140 times the distance to the Moon, but it's nothing compared to interstellar distances. Light takes only about 3 minutes to travel from Mars to Earth at closest approach, compared to over 4 years to reach Alpha Centauri. The difference is not merely quantitative, but qualitative. Mars missions are difficult, but feasible. Interstellar missions are, with current technology, effectively impossible. SpaceX, the private aerospace company founded by Elon Musk, has made Mars colonization a central part of its mission. The Starship vehicle, currently under development, is designed specifically for Mars transport. It's the largest and most powerful rocket ever built, capable of carrying over 100 tons to low Earth orbit and designed to be fully reusable, dramatically reducing the cost of space access. Whether SpaceX achieves its ambitious timeline remains to be seen. Space development has historically proceeded more slowly than optimists predict, but the mere fact that a private company is seriously pursuing Mars colonization represents a fundamental shift in how humanity approaches space exploration. For decades, space was the exclusive domain of government agencies with national prestige at stake. Now, commercial entities, driven by profit motives and visionary goals, are becoming major players. This diversification of space actors might accelerate progress in ways we cannot predict. Competition breeds innovation. Multiple approaches to the same problem increase the chances that at least one will succeed. The next few decades could see developments in space technology that make today's rockets look as primitive as the Wright Flyer looks compared to a modern jetliner. But let's be clear about what even the most optimistic scenarios entail. Colonizing Mars would be incomparably harder than anything humanity has ever attempted. The planet has no breathable atmosphere, with its thin carbon dioxide envelope providing virtually no protection from solar radiation. Surface temperatures average around -60 degrees Celsius and can drop below -100 at the poles. Dust storms can engulf the entire planet for months, blocking sunlight and coating everything in fine, abrasive particles. Early Mars settlers would live in pressurized habitats, venturing outside only in cumbersome spacesuits. They would eat food grown in artificial greenhouses or shipped from Earth at enormous expense. They would breathe manufactured air, drink recycled water, and depend on technology functioning perfectly for their moment-to-moment survival. A single equipment failure could prove fatal. A single supply ship lost could doom an entire colony. And yet, despite these daunting challenges, Mars colonization remains within the realm of possibility. We understand the physics involved, we have the basic technologies, even if they need significant refinement. The obstacles are engineering problems, not violations of fundamental physical law. Given sufficient resources, time and determination, we could establish permanent human presence on Mars within the next century. The same cannot be said of interstellar travel. No amount of incremental improvement to existing technologies will carry humans to other star systems. We would need fundamental breakthroughs in physics or propulsion that may never come. The distinction between difficult and impossible matters enormously when allocating limited resources and setting realistic expectations. This is why some scientists and space advocates argue we should focus our attention on the achievable rather than the fantastical. Instead of dreaming about warp drives and generation ships, we should be building lunar bases and Mars colonies. Instead of waiting for physics-defying breakthroughs, we should be maximizing what's possible with known science. The solar system offers enough challenges and wonders to occupy our species for millennia. Why pine for stars we cannot reach when unexplored worlds orbit our own sun? There's wisdom in this perspective, but also a certain sadness. Because the stars have always represented something more than mere destinations. They've symbolized possibility itself, the idea that no matter how constrained our current circumstances, unlimited horizons await somewhere beyond. To accept that we may never reach them is to accept a fundamental limitation on human potential, a ceiling on our cosmic ambitions. Perhaps this acceptance is necessary for maturity. Children dream of becoming astronauts, superheroes, explorers of infinite frontiers. Adults learn that reality imposes constraints, that not every dream can be fulfilled, that wisdom lies in pursuing achievable goals rather than impossible ones. Perhaps humanity as a species needs to undergo a similar maturation, accepting our cosmic limitations even as we maximize our potential within them. But I don't think acceptance requires abandonment. We can acknowledge the extreme difficulty, perhaps impossibility, of interstellar travel while still pursuing the research that might eventually make it feasible. We can focus on near-term goals like lunar bases and Mars colonies while still funding the fundamental physics that might reveal new possibilities. We can be realistic without being defeatist. Science has a way of surprising us. Discoveries come from unexpected directions, often from research that seemed purely theoretical or even frivolous at the time. The laser was invented without any specific application in mind and now underlies countless technologies from fiber optic communications to eye surgery. Quantum mechanics began as an abstract mathematical framework and now enables the transistors powering every electronic device on Earth. We cannot know what future discoveries might reveal about the nature of space-time, about propulsion possibilities we haven't imagined, about entirely new approaches to the problem of interstellar travel. Maintaining research programs in fundamental physics keeps these possibilities alive. Closing our minds to potential breakthroughs guarantees they will never come. The key is balance. We should pursue what's achievable while remaining open to what might become achievable. We should invest primarily in near-term space development while maintaining a portfolio of longer-term, higher-risk research. We should be humble about our current limitations while preserving the curiosity and ambition that have always driven human progress. This balanced approach reflects something important about human nature. We are neither purely practical creatures concerned only with immediate survival, nor purely visionary dreamers content to imagine without acting. We are both simultaneously, and our greatest achievements have always combined practical action with visionary ambition. The Apollo program exemplified this combination. It was driven by Cold War competition, a thoroughly practical concern about national prestige and technological supremacy. But it was also driven by the ancient human dream of reaching the moon, a vision that had inspired poets and storytellers for millennia. The practical and the visionary merged, producing one of humanity's greatest achievements. Perhaps something similar will be required for whatever comes next, whether that's sustainable lunar presence, Mars colonization, or eventually something we cannot yet imagine. We will need practical motivations, economic incentives, national interests, competitive pressures to sustain the enormous investments required. But we will also need vision, the ability to see beyond immediate returns to longer-term possibilities, the willingness to pursue goals whose ultimate value may not be apparent for generations. This brings us to a question that underlies everything we've discussed. What do we owe to future generations? The decisions we make today about space exploration, about fundamental research, about preserving or degrading our planet's environment, will shape the possibilities available to humans centuries and millennia from now. We are not just inhabitants of the present. We are ancestors of the future. This responsibility weighs heavily when considering long-term projects like interstellar travel. Even if we cannot reach the stars ourselves, we might develop technologies or knowledge that eventually enables our descendants to do so. Every investment in fundamental physics, every advancement in propulsion technology, every improvement in life support systems contributes to a cumulative inheritance that future generations will build upon. Alternatively, we might squander this inheritance. We might consume Earth's resources pursuing short-term gratification. We might destabilize our climate so severely that advanced technological civilization becomes impossible to maintain. We might destroy ourselves in conflicts over dwindling resources or ideological differences. Future generations might look back at our era not as the beginning of humanity's cosmic journey, but as the moment we foreclosed that possibility forever. The choices are ours, the responsibility is ours, and the time frame for making these choices is shorter than most people realize. The climate decisions made in the next few decades will shape Earth's environment for millennia. The investments made in space technology now will determine whether our descendants inherit a spacefaring civilization or a planet-bound one. The social and political structures we build will enable or prevent the cooperation necessary for any large-scale cosmic endeavor. This is the context within which all discussions of space exploration must be situated. We are not abstract beings contemplating theoretical possibilities. We are historical actors making consequential choices at a pivotal moment in human history. The path we choose will echo through generations. Some thinkers argue that space exploration itself might help us make better choices. The overview effect reported by many astronauts describes a profound cognitive shift that occurs when viewing Earth from space. Seeing our planet as a whole, without political boundaries, fragile and alone in the cosmic darkness, has transformed how many astronauts think about human civilization and its challenges. Edgar Mitchell, the Apollo 14 astronaut who walked on the moon in 1971, described it this way. You develop an instant global consciousness, a people orientation, an intense dissatisfaction with the state of the world, and a compulsion to do something about it. This wasn't unique to Mitchell. Astronaut after astronaut has reported similar experiences, a sudden recognition that national conflicts and political divisions are absurdly petty compared to our shared existence on a single, vulnerable world. If this perspective could be more widely shared, it might help humanity develop the cooperative institutions necessary for large-scale space development. Perhaps the path to the stars really does run through transformed consciousness, through a recognition of our common humanity that makes sustained collective action possible. Virtual reality and advanced imaging technologies might eventually allow more people to experience something like the overview effect without actually traveling to space. Educational programs emphasizing our cosmic context might shift cultural attitudes toward longer-term thinking and global cooperation. The very act of contemplating space exploration, regardless of whether we ever achieve it, might make us better stewards of our home planet. This is speculative, of course. Transformative experiences don't automatically translate into political change. Many astronauts who reported the overview effect returned to Earth and resumed normal lives without dramatically altering their behavior or beliefs. Cultural and institutional inertia is powerful. Individual insights, however profound, often fail to reshape social structures. But ideas matter, visions matter. The stories we tell ourselves about who we are and where we're going shape the choices we make. If we collectively embrace a vision of humanity as a spacefaring species, as cosmic beings with responsibilities extending beyond our immediate concerns, we might act differently than if we see ourselves as merely consumers competing for scarce resources on an overcrowded planet. This is one reason why science fiction matters, why popular depictions of space exploration influence real-world outcomes. Star Trek inspired a generation of scientists and engineers to pursue careers in space-related fields. Carl Sagan's Cosmos television series sparked wonder about the universe in millions of viewers. The vision of humanity reaching for the stars, even if scientifically inaccurate in many details, creates cultural momentum toward actually doing so. We need new visions now, visions that acknowledge the real difficulties of space exploration while maintaining the inspiration to pursue it. We need stories that portray not effortless travel between stars, but the genuine challenges and sacrifices involved. We need heroes who are not just dashing adventurers, but patient scientists, dedicated engineers, and ordinary people willing to dedicate their lives to goals they may never see fulfilled. The Mars colonization effort, if it succeeds, will require exactly this kind of heroism. The first settlers will face hardships we can barely imagine. They will live in constant danger, far from everything familiar, knowing that rescue is impossible if things go wrong. They will be not conquerors but pioneers, not masters of a new world but humble students, learning to survive in an environment utterly indifferent to human needs. Their story will be different from the adventure narratives of science fiction. It will be a story of persistence, adaptation, and gradual progress. It will unfold not over seasons of a television show but over decades and centuries of real history. It will include failures and tragedies alongside successes and triumphs, and it will be written not by individual heroes, but by communities of people working together across generations. Perhaps this is the most important lesson that contemplating interstellar travel teaches us. Whatever we achieve in space will be achieved collectively through sustained cooperation extending across generations. No individual, no single organization, no nation acting alone can accomplish what needs to be done. The scale of the challenge demands a scale of response that transcends our usual categories. This is simultaneously humbling and inspiring. Humbling, because it reveals the limits of individual action, the inability of any one of us to significantly impact outcomes that will unfold over centuries. Inspiring because it connects us to something larger than ourselves, a multi-generational project that gives meaning to efforts that will never be personally rewarded. The builders of medieval cathedrals understood this. They dedicated their lives to structures they knew they would never see completed. They worked not for personal glory but for future generations who would worship in spaces they had created. They found meaning in contributing to something that transcended their individual existence. Perhaps this is the attitude we need to cultivate, a willingness to work for futures we will never experience, to plant trees whose shade we will never enjoy. The Interstellar project, whether or not it ever succeeds, might be valuable precisely because it demands this orientation. It forces us to think beyond our lifetimes, to consider our place in a chain of generations extending into the indefinite future. And who knows, perhaps our distant descendants, inheriting the accumulated knowledge and technology of thousands of years of human development, will find ways to reach the stars that we cannot imagine. Perhaps they will look back at our era as the beginning of a journey that eventually spanned the galaxy. Perhaps our struggles and sacrifices, our seemingly futile reaching toward impossibly distant lights, will prove to be the first steps on a path we could never have foreseen. Or perhaps not. Perhaps humanity will remain forever confined to this solar system, a single species on a handful of worlds orbiting one unremarkable star. Perhaps the interstellar distances will prove permanently unbridgeable, the speed of light an absolute barrier that no civilization anywhere in the universe has ever overcome. Perhaps our dreams of reaching the stars are simply that, dreams, beautiful and inspiring, but ultimately unrealizable. The philosopher Blaise Pascal wrote about the terror of infinite spaces, the vertigo that comes from contemplating a universe that dwarfs human existence into insignificance. But terror is not the only possible response. There is also wonder, gratitude, humility, and a strange kind of peace that comes from accepting our place in the cosmic order. We are small, yes, we are temporary, we are confined to a tiny corner of an incomprehensibly vast universe, but we are also the universe becoming aware of itself. We are matter that has learned to contemplate matter. We are the cosmos asking questions about its own nature. In us, the universe has developed eyes to see itself, minds to understand itself, hearts to feel awe at its own existence. This is not nothing. This is perhaps the most remarkable thing that has ever happened in the history of everything. Against all odds, in one corner of one galaxy, chemistry became biology, became consciousness, became curiosity. We exist, we think, we wonder, we ask why. If you made it this far, make sure to subscribe to the channel and give a like. And how far can we actually travel in space? If you're fascinated by interstellar travel, Mars missions, space colonization, advanced propulsion systems, and humanity's future among the stars, this ultimate guide will transform your understanding of our place in the universe. See you there.